Good evening, everybody, in person and online. Welcome to the Adirondack Sky Center and Observatory's technically first event of Totality and Tupper. We're pleased to be doing this at the Wild Center. We've had a great partnership with them throughout this entire Totality and Tupper planning and execution. We're looking forward to the next few days. So before we get started with tonight's program, I just wanted to tell you a little bit about the Adirondack Sky Center and Observatory. The question always is, why did we build an observatory in Tupper Lake? Well, if you look at this dark sky map of the Northeast, you'll see that there's a particularly dark area right in the middle of the Adirondack Park. And that really just means that we're farther away from these metropolitan areas that bleed light into the night sky. And if you're interested in astronomy at all, you know that light is the enemy of astronomers, including sometimes the moon at night. So we're in the middle of that band, that ring of light that surrounds the entire Adirondack Park, from Montreal and Quebec down to Rochester, Syracuse, Albany, Boston, and down to New York. And on any given observing night that we host the public, we have people from one or many of these cities that come specifically to Tupper Lake because of the dark skies here. And it allows us to provide excellent viewing opportunities for anybody who's interested in seeing things, 58 million light years away, for example. It's a great opportunity. And because we're not restricted by the light pollution, we just enjoy that even more, and so do our visitors. So a little bit more about our mission. We're really dedicated to making astronomy and the universe more accessible to everybody. I say, my background is not astronomy. I was a music teacher and a school administrator and a technology guy. Never did I take any courses in astronomy or even science for that matter. And so I say you don't need an advanced degree in astrophysics in order to understand your place in the universe and feel comfortable with where you live. It's all our universe, and we believe people should feel relaxed and comfortable and part of that universe without being intimidated by things that we see out there. We do that through a number of outreach programs. We do public observing nights, any clear night that we can these days. We try to grab them when we can, typically on Friday. It starts just like this, with a presentation, an overview of what we would see in the night sky that night, and a little bit of a laser pointer show as to where those objects are in the sky. Sometimes there's themes like planetary nebula or galaxies during galaxy season and so forth. And we point those out to viewers. And we show them some of the deep space images that we've taken right from the roll-off roof observatory of what those objects look like. So when they go inside and they look through the telescopes, they can see more of what they're looking for. It's not a mystery, what am I trying to see here? They already know this is what you're trying to see. And it's nowhere near as vivid through the eyepiece as it would be through a camera. So we also do private parties. This is a 13-year-old birthday party parents got for their child. We host anniversaries there, family reunions. A few weeks ago, there was a gentleman who got down on one knee and proposed to his girlfriend at the end of the night, and had a nice romantic time there. So it's nice. All sorts of, you can rent it for any reason. It's basically rent an astronomer for a night, and we take you through the night sky. We do a lot of outreach to schools through our portable planetarium. The Star Lab travels all throughout the Adirondack Park to schools and other places as well. And students get to go inside and have a planetarium-like experience during the school day. That's not something that most of them have the opportunity to do. In addition to other STEM-related activities, planetary motion and other STEM activities that relate to astronomy. We have a number of after-school programs that go on, summer camps. This is an activity for parents and children where they got to make their own telescopes. And I was saying just before the talk, this little girl made that telescope and then came up to the observatory that night and was able to see the rings of Saturn through that telescope. And you see how excited she is just in making the telescope. You can imagine how excited she was when she got to see Saturn through the telescope. We host an annual astrophotography conference. It's a 4-day immersive experience, so no matter what level you're at in astrophotography, we take you to the next level. We work with you on your equipment, on your files. Typically, we go out at night and shoot, get data files, and then the next day we bring them in and process them in a computer lab, like you see in that middle picture. And it's a very satisfying experience. Everybody really gains a skill. And if you're a beginner, you get better. If you're an advanced user, you pick up things that you've not been able to do before. And again, it's very immersive. So there's somebody standing right with you, helping you solve problems. 4 days, that kind of an experience, $300 experience. There's nothing in the country, honestly, that I know of, or nothing I've ever heard of that is like this. We also do our online lecture series called the Cygnus Series. That happens the first Thursday of every month at 7 o'clock. And we have guests from all over the world at this point, and now viewers from all over the world. I think we have one standard guy from Nigeria tunes into almost every lecture that we do, so we can always count on him to be there. So that's all, again, all of this free to the public. We don't charge for any of this kind of stuff. And there's a view of our current observatory. That's a roll-off roof observatory. That green roof weighs about 4,000 pounds, and it rolls off when we're ready to use the telescopes. And then when we're done for the night, we just have a motor, we press a button, and it rolls back on. And in there you can see those 4 permanently mounted telescopes. Again, you can see deep, deep space with those. These are not Walmart-level telescopes. They're big stuff. But the more exciting news is that we're embarking on building a planetarium to add to that observatory, and will be one of those rare sites where you have an observatory and a planetarium on the same site. Typically, not always, but typically an observatory would be located at the top of a mountain someplace where the air is thin, the sky is clear, and the planetaria are typically located in the middle of Boston or Rochester or New York. We'll be one of those few sites that have both, so we'll be able to have year-round and 24-hour service, so to speak. And it'll be located right on our site. There's the roll-off roof observatory currently, and that's where the site of the planetarium will be. It's the second phase of a much larger project, but that's being planned currently, and we're pretty excited about it. It'll contain the planetarium, but also a full classroom, lecture hall, other exhibits and activities for folks to do. And here's just your standard kind of side view. We're done with the initial planning and the pre-design phase, and we'll be moving into the actual mechanical drawings not too long from now. And here's your standard. This is what it looks like. So this is not our planetarium, but this is just a rendering of what we expect it to look like. Completely digital, state of the art. Not only limited to astronomy, by the way. We can go on field trips to the Great Wall of China, or we can go inside of a planet someplace. So it'll be very exciting. Anyway, that's the Adirondack Sky Center and Observatory. That's what we do, and hopefully you've heard of us before. The more and more we get out there, the more our name gets out there, and people are becoming reliant on us for information, for programs, especially because we're the only astronomy-based organization in the Adirondack Park. So we've become the eclipse go-to people. And we've created this event coming up called Totality in Tupper. It's a community event, including the Wild Center, the Arts Center, the library. We've got partners all throughout the community, all creating this massive event celebrating the total eclipse of the sun coming up. So that's here this weekend. I'm hoping that many of you will be participating in the experience. Our event is being held at the elementary school just across the fields here. acres and acres of property there to be viewing from, and some other fantastic activities, solar viewing, big digital screen, food trucks, all sorts of great things going on there. So that's that. The reason we're here tonight is for our first of the activities for Totality and Tupper for the Adirondack Sky Center, and that is having Dr. Ed DeLuca here with us. And I won't take too much time, but Dr. DeLuca is a retired senior scientist at the Smithsonian Astrophysical Observatory. He's also done extensive research on the role of active region of magnetic fields on the structure and dynamics of the solar corona. So what better person could we ask to come up and share some of his expertise with us? So with that, I'd like to welcome Dr. Ed DeLuca to the podium.
Thank you for that, and thanks for the invitation to this party at Totality and Tupper. I mean, I think we're going to have some fun days coming up. So I'm going to give sort of a technical discussion as to what heliophysics is at NASA. And my background is in solar physics. I have a PhD in astrophysics, but really that, the only astrophysical object I've spent any time studying in any detail is the sun. And I've never been employed by NASA directly, but my funding the vast majority of my funding has come from NASA. There's been some NSF funding as well, and there'll be another talk that talks about some of those interesting projects. And so NASA has the Science Mission Directorate of NASA does astrophysics, earth science, planetary science, heliophysics, and then they have a sort of a biophysics, related to human biology, but a smaller physical science and space program. The heliophysics division is relatively small in terms of funding compared to the others. Part of the reason for that is our remote sensing instruments look at the brightest thing in the sky, which is the sun. So you don't need as large a telescope when you're looking at the sun as you do if you're looking at something far away and faint. The other aspects of it are in situ measurements, and we'll talk about Parker Solar Probe, which is a satellite that was launched recently and is up now and is the fastest thing that has been built by humans. It's gone closest to the sun, and it largely does sampling of the solar atmosphere in situ. So it's actually measuring particles. So there are two aspects of these, and then there's the part of heliophysics, which I'm going to talk less about, is the Earth ionosphere, magnetosphere of the Earth, the impact of solar events on our terrestrial environment. But we'll get into all of this. So since it's kind of technical, just interrupt me if you've got questions. If I'm going down a rabbit hole and you don't understand what's going on, ask me, because I probably can explain it. I just am not explaining it clearly, evidently, if you don't understand. So this is what heliophysics is, as far as the National Academy of Sciences says in their reviews of heliophysics, right? This is the charter, if you will. What is NASA supposed to be doing? It's supposed to study the sun's influence on the Earth and the solar system out to the interstellar medium. So that's reasonably confined as far as astrophysics is concerned, but it encompasses all of the planets and out to the edge of the atmosphere, edge of the heliosphere, where the interstellar medium starts. And it's also supposed to use the solar system as a laboratory for astrophysics and exoplanet studies, right? Because we can see the sun better than we can see any star. We can actually sample into the interplanetary medium. It's going to be similar to stellar winds. We can sample the outer atmospheres of planets. It's going to be similar to exoplanets. Our own planet is similar to exoplanets. And so understanding these systems in some detail allows us to interpret other things that we don't have such great detail on. But the other things are much more varied, right? We have one star, right? We've got the sun. And there are lots of other stars that are doing different things. And so there are similarities and differences. And what are you pulling out from the sun to understand how other stars behave, how the eruptions from the sun, what we call solar mass ejections, those happen on other stars. We've seen them on other stars. They're hard to see. How do those differ? How are they the same? So that's part of the charter. And finally, there's an applied aspect of our field because the sun drives what we call space weather. So there are solar events that impact the Earth and can have adverse impact on satellites, on radio communication, on ground currents. It can bring down transformers and aspects like that. So trying to understand that science so that people who are doing space weather forecasting can improve their models. So we're doing the physical basis behind the space weather forecasting. National Oceanic and Atmospheric Administration is charged with doing forecasts. They do the national weather forecast. They also do space weather forecasting. So that's their responsibility. NASA's responsibility is to develop the scientific basis for improving the forecasting. So that's part of their charter. All right, so we're going to learn all about the sun in a single slide, and then we'll move on. So in the core of the sun is where all of the energy that generates life on Earth originally happens, right? Hydrogen is converted into helium, right? That's in the core here, this bit there, and releases energy. Now, that energy has to get out, right? It's only happening in the very core of the sun where it's very dense and very hot, and so you can combine four protons together to get a helium nucleus. So what happens is the energy is transferred out. Do I have a pointer? I must have a pointer. Yes, I have a pointer. But this is not going to work for the people online, so I will use this pointer. Okay, you can see the arrow perhaps. Right, so the energy is released here in the core, and then there's a radiative transfer. So it's essentially photons are moving the energy from the core. Generally, the atmosphere is cooling off as it goes out, and it's photon collisions that are happening. At some point within the envelope of the sun, it cools enough so that hydrogen is not completely ionized. So there's electrons formed into hydrogen atoms. And when that happens, it's really inefficient to transfer energy by radiation because radiation will just excite the electron and it then will collapse and it'll excite the electron. So it suddenly gets really challenging for the energy to get out. And so heat builds up. And what happens is you then start moving energy out through convective motions. And so it's like an overturning like you see when you're boiling miso soup, for example. If you have a nice hot bowl of miso soup, you blow on the surface, you'll see these beautiful little convection patterns because you've got the little bits of particles in the soup that show where the flow is happening. And so it's cooling by convection. Why is that important? Who cares, right? At one point it gets out to the sun is hot at the end, and that's all you need. But the convection zone is crucially important for generating magnetic fields. And what we're going to see throughout the rest of this talk, and hopefully on Monday when you look at the corona, is the impact of magnetic fields on the solar corona. The existence of the solar coronas, the structure in the solar corona is all due to the magnetic fields in the sun, and they're generated in the convection zone. And it's a hard problem. It's one of these weird problems that it turns out all of the physics was understood at the beginning of the 1900s for the mathematics of this problem. Everybody understood the equations. And it wasn't until well into the 1950s that the actual, how you can get a fluid, which is what this gas is that's convecting, a conducting fluid that's simply connected to generate a magnetic field. If you write down equations of motions, typically, and there are a lot of people, very good mathematicians, writing down equations, all of them were unable to maintain dynamo action against diffusion. And there are these anti-dynamo theorems in mathematics. This flow, this type of motion will not maintain a magnetic field. So how did these things happen? And so Eugene Parker came up with the notion that, in fact, it have to have a lifting and twisting motion to generate a magnetic field. And suddenly there was this explosion of understanding. But that happens uniformly. Everywhere in the universe, there are magnetic fields generated in these simply conducting plasmas, right? It's not like you've got a wire where you're running a current through it. You've got this fluid that is electrically conducting, and you're moving it in such a way that you can generate currents in it without shorting them out. It's really quite fun. And so that generates magnetic fields, and now we get to the surface. So those magnetic fields, when they erupt from the surface, they form sunspots. Sunspots appear dark in visible light. They're dark because they're cooler. They're cooler because the strong magnetic fields actually are strong enough at this point to inhibit the convective motions. So the transfer of heat is reduced through the sunspot. The cooling happens at the top, not as much heat at the bottom. It's cooler. The result is cooler than the surroundings. So sunspots are darker than their surroundings because they're cooler, but they're also outlining regions of strong magnetic fields. And once these magnetic fields erupt into the solar atmosphere, then you end up with the corona. And so that's what we're going to be sort of looking at and hopefully seeing on Monday. All right. A lot going on. But this is the picture, right? And this is, if you want to understand why anybody is interested in studying the sun, that's why, right? Because it's really, really, really beautiful. And this is an image from a Belgian satellite. It's highly processed, but what you're seeing here is gas of roughly 1,000,000 degrees Kelvin, 1,000,000 degrees Celsius too. And the sun is rotating, right? The sun rotates, the earth rotates. And bright things here, all of the gas is about the same temperature, but bright things here are denser. There's more gas along the line of sight than the faint things. They've cheated a little bit by having a different color scheme in the outside than on the disk, just so that the contrast is flattened, because the things on the disk are probably 1,000 times brighter than the things out here. But they are connected. And so to see the connections, you kind of have to flatten, do some playing with the scales. So what are we seeing? We're seeing magnetic fields on the surface, these active regions. They're emerging and connecting out into the outer corona. We're seeing large-scale structures that persist and rotate around the sun. The sun is rotating on the right, like a right hand, and these fields are opening up into planetary space. And we're going to have a couple of different movies. This was the first one of its kind back in 2014. Now, our friends at NOAA have built a satellite, the GOES satellite, which is part of their space weather operational system, is also used. They did some special off-pointings so that this is the typical GOES field of view here. And then they take another set of images where they're looking out to the edge. So you can see further out. And you can see how the magnetic structures, some of them stay confined, some of them collapse back in, some of them erupt out. There is you might notice the fields up at the top here. These are the magnetic poles of the sun. So the sun does have a dipole field in it. So there's a north pole and a south pole. They change every 11 years as part of the solar cycle. And the fields there really extend into interplanetary space, right? The fields in the middle are created by these active regions that are erupting, have strong magnetic fields, and so those are where the dynamic events like flares and coronal mass ejections occur from those active region fields. I'm going to play this again. The two different images, this is about plasma of about 1 million degrees. This is plasma about 1.5 million degrees. And you can see that there are differences, not just in the color table. The color table is a false color. These are all just black and white images. But you can see that the bright structures there are similarities, but this structure here is not seen there. Right? And there are things that are seen in the hotter channel that aren't seen in the cooler channel. Now, these dark regions here are what we call coronal holes. That is, you're not seeing, they're dark because there's no hot plasma along the field of view. And what's happened there is, because the polar fields are open into interplanetary space, the plasma on them is never very dense. Right? The densest regions have these closed magnetic field structures. Well, let's just pause it. Oh, sorry, we'll pause it here. That's not a good one. Sorry. We will pause it. I don't know. Where are we going to pause it? I'm not liking this movie anymore. Okay. Well, this structure here, right? So these are compact loops. It's very bright. And there's hot plasma there, but the magnetic fields are closed at both ends. And so when you start filling it with plasma, it can't escape. Whereas the magnetic fields here are opened into interplanetary space, and so the density is much lower. So that's sort of the basic, giving sort of an idea of the global magnetic structure here. This is exactly the same data combining the two images, and it's just a pretty movie. But you can also see in the different colors how material ablates into there's a little coronal mass ejection there, how material expands into the interplanetary space, right, into the solar wind. And so that's the sort of the next bit that we need to get into, is what is the solar wind? All right. So the solar wind is generated because the atmosphere in the corona has a higher pressure than interplanetary space, right? So the wind is being driven by the heat and the pressure of the coronal magnetic field, the coronal gas, and so the gas expands and out into interplanetary space. Now, as you saw, the sun is rotating. Those magnetic fields some of the one end of the magnetic field is tied into the sun is rotating, and so you end up with this sort of effect like a sprinkler nozzle that's rotating. It's the water is trying to go out, but you'll see it as a curve structure, and so this is the spiral structure of the solar wind. Again, Eugene Parker, same person who came up with the solution for the dynamo problem, came up with this solution. And he has a satellite named after him So what we do now is we have these models that are based on observations of the solar surface, our understanding of physics, and with these projections are really what scientists and forecasters also use to interpret observations and to plan observations. So we're seeing here, this is a density plot, high density streams coming out from the sun, low density streams in between them, and this is the Earth, and these are different satellites, stereo A and B. And here is so this is looking down from the top, and this is looking from the side. So here's the sun there, and now this is up and down in the plane of this plane here. This is the vertical view, right? So you can see that here there is a structure out of the plane that is dense and below the plane, and this is the velocity. So this is density and velocity, and sometimes there are relatively low dense fast streams, and sometimes there are high dense fast streams. Right, so and these over here are actually showing you traces of, at a particular time at the Earth, at these points what are you seeing? So this line, when we show that as a movie later on, you'll see that this line will move across as this is evolving, and you'll see the structures. So that's sort of the actual, the previous one was sort of the idealized view of this Parker spiral, the solar wind, and here is a model based on observations that's continually sort of updated. It's a data-driven model of the solar wind. Right, now the solar wind then hits the Earth. Now the Earth also has a magnetic field, right? So the magnetic fields are kind of the dominant theme here. And what happens is the sun's magnetic fields hit the Earth's magnetic fields. There's plasma here, there's plasma there, and they wrap around, right? Because this is a conducting gas, they cannot just flow through. And at some point, depending on the direction of the sun's magnetic fields and the Earth's magnetic fields, they can reconnect. So this is a magnetic field line that's coming down. There would be an opposite red magnetic field line coming up and a white magnetic field line coming down there. Those field lines can reconnect, release energy, and then this new half red, half white field line is going to be pulled back through the magnetosphere into the magnetotail. And so this is sort of the dynamic interaction between the sun's magnetic fields in interplanetary space and the solar wind and the Earth's magnetic field. And the Earth is also rotating, right? So as this is going on, the Earth is rotating and these field lines are moving as well. So we'll have a simulation of that later on to see how that works. So that's the impact on the Earth's magnetosphere, and then eventually, if there is an event, you might see aurora, and depending on how intense the emission is, you may see aurora in different colors or different pass bands, depending on where in the atmosphere those high energy electrons or particles are coming into. Okay, so here's a movie that's, this is going to be a movie of that similar model, but we're now focused, this is done by our friends to work with Parker Solar Probe. So this is kind of all about how is the solar wind interacting with Parker Solar Probe, which is here. And it's, that's Venus, but it's near there at that point. And it's in this picture, it will always stay right here in this rectangle. This is then the measurement of the actual radial velocity at Parker Solar Probe. So you're able to compare these data-driven models with an actual observation. This is the planet Venus, so Parker Solar Probe is now, is near Venus. These black and white lines here are showing the connection of this is a sort of a magnetic field line as it's connected back to the sun. And so the question is, the Earth is on this magnetic field line and Parker Solar Probe is on that magnetic field line. Stereo A is a different satellite, is on this magnetic field line, right? So let's look at the movie and then we'll see how confusing it is. So everything is rotating. There's an event moving past, and here's Venus is moving, but Parker Solar Probe is there. The field line is fluctuating, and as a high pressure system goes through, you see the bump there, and now we're getting down into a low pressure, low velocity system. And all of this is happening over, days. Is the date here in date and hours. So you can see that Parker Solar Probe, this little rectangular box from the end of the movie to the beginning of the movie has rotated, right? This rectangular box, which is what we're seeing here, is actually rotating around the sun, because as Parker Solar Probe moves in, it picks up speed, and it's separation angle from the Earth changes. So now it's in line with the Earth, but they're on different magnetic field lines, and now it's ahead of the Earth. This is the radial line that's going out from Parker Solar Probe, and so this is kind of the data sets that people who are doing the science in the heliophysics division are looking at on a regular basis, both sort of interpreting observations that they have and trying to plan coordinated observations for the future. When we expect Parker Solar Probe to be near the sun and on a field line adjacent to the Earth, we have a lot of assets always near the Earth, so we can look at how the solar wind is changing from very close to the sun to reasonably far away from the sun. Okay, these models are here, and they're available. They're not intended for public view, but you can look at them and they're really pretty, and they have them all the time. And it's just interesting to see these things. Here's a simulation of what happens to the Earth's magnetosphere when one of these events. So this is the Earth down here. There's Australia, and this is that was the Milky Way. So now we have a solar wind, a CME hitting the Earth and generating these plasma particles. Then these field lines are draping around the Earth. So it's highlighting the Earth's magnetic field and the magnetic fields of the solar wind, and these sort of dynamic reconnection events that are creating density fluctuations in the magnetosphere, which can also be seen as aurora formation. Field lines in the tail get reconnected and pinched off and flow back. They get stretched out and energized again, and then as they relax, they get shortened and release energy into the poles. So these kinds of dynamic modeling is something that's really state-of-the-art types of simulations. It requires a lot of computing power. It requires a lot of data assimilation, but it allows you to compare in detail the model predictions with actual satellite observations. You can see the Milky Way there. So this is really just a lovely movie as well. So here are the heliosphere. This is the mission suite, as it were, for the science mission. It's for the heliophysics division. And there are a lot of satellites. I mean, obviously, this is not to scale distance from the sun to the Earth. It's just highlighting that we do solar things, we do Earth's magnetosphere things, we do some things on Mars. This is Mars hanging out, looking at the solar impacts on Mars. And there's Voyager down at the bottom, which has left the heliosphere entirely. But I think we still take credit for Voyager at some point. So of all of these missions, I'm going to talk in some detail about Solar Dynamics Observatory. We've already seen some images of theirs, and we've seen some and discussed Parker Solar Probe in a little more detail. I spent a lot of my career working on the X-ray telescope on a Japanese satellite, the Hinode. It's a joint NASA, JAXA, and UK mission. And I was involved in the proposal aspects, and our group built the telescopes for IRIS as well. But I'm not going to go into any particular details about those. We'll close with a quick discussion of MUSE and HelioSwarm, which are two new missions which have not yet flown, and our institution is actually involved in both of them. They're really different missions from each other, and so they're giving you a sort of a sense of the range of things that NASA's doing. Okay, so Solar Dynamics Observatory is a strategic mission from NASA's point of view. So this is $1 billion mission. It's in an orbit that is sort of a stationary orbit between the Earth and the Sun. So it doesn't actually, the Sun is never eclipsed by the Earth. It sees the sun continuously. It has its enormous ground station in Arizona and pulls down terabytes of data every day. And so it's taking images of this, the coronal imagers are operating on a 12-second cadence, the whole sun in multiple channels, in 8 channels. And then there's a magnetograph that's also taking data equally frequently. So it's just massive in their 4K by 4K CCD images. So why did anybody bother to do this? Right, so they want to understand how the magnetic field is generated and structured. So that's observations of the surface magnetic field of the sun and measuring waves in the solar photosphere, helioseismology, which I'm really not going to get into, but allows the interpretation of those waves allow you to sort of image inside the sun by looking at how the waves are interacting with the magnetic fields. And then how this, the sort of the coronal aspect of this is how the energy is stored and converted and released into the heliosphere and geospace in the form of solar wind, energetic particles, and CMEs, of course. Right, so it's a big telescope, right? I mean, for $1 billion, you get a big telescope. And you have to launch it on a big rocket. This is the atmospheric imaging assembly. These 4 telescopes were built at our institution. The prime contractor was Lockheed Martin, and we did the telescopes, they did the electronics and the cameras, and we've had really, really strong collaborations with them for almost for my entire career there. It's really been a very good working relationship with us. This is an artist's rendering. There's our 4 telescopes again. So the 4 telescopes each have 2 different pass bands, so there are 8 channels in the 4 telescopes. And this is what the images look like. So these are magnetograms and continuum observations from a separate telescope, the heliospheric magnetic imager. So that does magnetic field measurements in the photosphere, and it does visual images, and it does these wave observations of surface motion of the photosphere, Doppler maps. And then these are all of the AIA images, right? So some of these are selected by filters, these 1700 angstrom, 2500 angstrom, 1600 angstrom. These are single passband that have different focal plane filters that allow you to select out those. Then you have a helium image, which is, this is a relatively cool chromospheric plasma, and the rest of these are coronal, right? So these guys here are kind of looking at a little bit above the visible surface in temperature. You can see sort of the temperatures that they're indicating here are going up. So getting all of these images every 12 seconds for the whole sun allows you to do remarkable things. And one of the things that people notice is that there are events that happen on one side of the sun that then trigger events on the other side of the sun, really far away. And the only way that that can occur is through a global magnetic connection in between those places that's altering. All right, so something is changing something is, say, erupting here, and it disturbs a large-scale magnetic structure that causes an eruption someplace else. And we've seen this many, many, many times. And it's one of those things that if you didn't actually see it initially, people wouldn't believe it was possible. The other instrument on there is a spectrograph, which looks at the sun as a star, and that's the EVE, is the EUV spectrograph. And so it takes images of so how particular lines brighten and fade as energetic events happen. So these are images from the AIA channel. So these are flare images, and then this is showing how the flare lines are changing in time in hours at the bottom. Okay. So these are two different temperatures. Is this going to fly? Okay. So this is the sun in two different temperatures. So this is about 1,000,000 Kelvin. This is has the bright stuff here is about 10 million Kelvin. The faint stuff that's around the edges is cooler. And so you're just looking at sort of the difference in morphology of hot and cool plasma, or warm and hot plasma, as we really should call it. And the filamentary structure in the hot plasma, there are some, the radial expansion is much more dramatic at 1,000,000 degrees. You see these bright structures and these large-scale loop structures. Things are more compact in the hotter channels. And there is some indication of hot plasma escaping into interplanetary space, but a lot of these are closed loops. Let me move on. Up. There we go. Up. This is come on. There we go. This is a Parker Solar Probe now. So this is fastest man-made object. It's the closest object to the sun, and it is able to do this because of some very interesting mechanical materials, composite materials, that are able to withstand that heat. But the part of the instrument that was built at Smithsonian actually is not behind the heat shield. And one of the, I was there, I wasn't involved directly in this project, but I was observing the building of this instrument. And what they had to do to demonstrate that the Faraday cup has to see the solar wind directly. It has to sample, it can't see it from behind. It has to sort of be facing the sun in order to get the material that it needs to sample the solar wind. And that means it's, it's exposed to all of that radiation. So NASA's not going to let you build that and fly that unless they have some reasonable certainty that it's not just going to melt, right? And so we had to test that at Smithsonian. And one of our engineers essentially acquired these large high-definition projector cameras that they used to use for the IMAX cameras, right? They don't use them anymore because everything's digital now. But you did the calculation that if you had 3 of these, you could generate the intensity of the sun at 9 solar radii on your little piece of engineering model of your Faraday cup. And so he did that. And you can imagine that building this in a laboratory does involve some risk, right? Because you don't want people to be exposed to that bright light. And so he had various, there were filters on this so that, it was sufficiently bright that you can't look at the experiment as it's happening. So everybody needs to be wearing these welding goggles. And you can't even know if it's aligned easily. So he took these various plates of metal and used them as a sort of, if you're aligning a telescope, you put a card stock and you try to see where the light point is so you can focus it. So he would do this with these sheets of aluminum and they would just evaporate. So he finally got a cooling plate so that you could actually keep the plate sufficiently cool by running water through it. And then you could align these things so that you could actually set up your and do your experiment. But we have all of these plates, these melted plates of the previous failures. And finally, when they were doing this, this is an odd thing about city government. The city of Cambridge was wondering, where is all this hot water coming from? Why are you generating all of this hot water in your lab, right? Because we shouldn't be seeing this. And it's actually a form of pollution. And so we had to actually, cool the water before it went into the public, sewer system, because somebody noticed. So anyway, so these engineering things are really interesting, and so Parker Solar Probe works. This is a movie of sort of, this is what Parker Solar Probe is doing. This is one of those nice GOES movies behind, and white light coronagraph image over there. And we're going to see this, I think this, so our Faraday cup is this little bit poking out over the edge. There's the heat shield. That's the sun. It pointed at the sun. And the solar panels actually should be folded back when it's close to the sun. They're a little bit, that's not quite right, because they can't, when at closest approach, they're almost behind the heat shield as well. So that's one bit, and there's our engineer, Tony Case. This is the life-size flight model of the Faraday cup. So this is the part that's exposed to the sun. Then this part is behind the heat shield, and you have to have some also very interesting mechanical properties and conducting properties in these wires that are going from something that's thousands of degrees down to something that's essentially hundreds of degrees over here while still carrying the signal and not creating electronic noise and not melting. So all of that was done, and this is giving you a sense of where this is the sun. This is how many solar diameters the Earth is, Venus. The sizes of the Earth, Venus, and Mars obviously are not the same, but this is just showing you how far away is the Earth in solar diameters. And so there's Parker Solar Probe. Let me see if I think that was supposed to, okay, well, anyway. So Parker Solar Probe is now 12 solar diameters away, and it will be as close as 9 when it gets, but this is at encounter 19. So for this eclipse, that's where it's going to be. There we go. And the other, now there's also an imager on Parker Solar Probe, and this imager is not looking at the sun because it can't, but it is looking at, if the sun is there, it's looking at right angles to the sun. So it's seeing the material that's going to be flowing, that the Parker Solar Probe will be passing through as it before it gets there. So it's called the wide field imager, and it's a visible light imager that looks at the solar wind in interplanetary space. And the movies here, again, U.S. Naval the Naval Research Lab, WSPR spelled weirdly, .navy.mil. Again, these are, these movies are available, and they're just loads of fun. So this is plasma from the solar wind coming out. This is a planet, I think probably Mercury or Venus, I don't know. And there's going to be an event, and the streaks are high energy particles that are hitting the camera. And there's a CME that's coming out through there. And so this is what, and this is the Milky Way there. These are probably stars. So you get a sense as to how tenuous the gas is and how dynamic the gas is, and all of these structures that are in this solar wind, and the billowing nature of this thing. And so this is being produced on regular cadence. For every encounter, they produce one of these video composite maps to show you how is the solar wind relating to that encounter. Whoops. Okay, so going to change a little bit to go into the final aspect of this is the space weather side. And some of that is related to, okay, so this is the close-up of today's sun, the magnetic fields on the sun today. Light and dark are different polarities, positive and negative polarities. And so these are active regions. There's probably sunspots here. The active regions have numbers. So the older active regions are decayed down here and they don't no longer have numbers. And this is the 1.5 million degree plasma associated with this sun. So this is up in the corona. This is down on the photosphere. And you can see there are some coronal holes and some structures there. From that, the friends at Predictive Sciences have forecast what will we see at Tupper Lake. This is the particular view from Tupper Lake of the corona, right? So this is the structure with the solar north this way. So your angle up depends on the how your telescope is oriented, where the clocking of this. But they just put the solar north up. That is an image of the moon that they placed in front of the sun. So this is the structure that they are forecasting based on the surface magnetic field evolution over, I think, a 12-day period. And we'll see the evolution of that movie. But this, again, these maps are available there. And so here this is the movie of how the sun is evolving toward their prediction. So these are data being assimilated. Here's the date from the March 19th. And you can see that this is their modeling forecast of the structures in the corona over time, right? And you'll see that some of these structures, the large-scale structures, are moving from right to left, and some of them are moving from left to right. And but we know the sun is rotating only in one direction. So it's whether the structure is in the foreground or the background, right? So if the structure is rooted on the front of the sun, you'll see it moving from left to right. If it's rooted in the back of the sun, you'll see it moving from right to left, right? So, so that's fun. And then because their model actually is dependent on the magnetic structure, so this is the magnetic field model, and it's something called the squashing factor Q, but it's essentially telling you where are the fine structures in the magnetic field that that are essentially defining the magnetic topology. And so you can see that there are field lines that are radiating into space, there are field lines that are closed, and there are field lines that transition from being closed to open over the course of this time. And this large-scale magnetic structure is what produces this visible light pattern, right? So this is where the physics is going on in this colorful image, and this is the result of that simulation. And finally, so now we're back at our constellation. And we're going to just do a couple of quick things on the future missions. Excuse me. So these are what NASA calls mid-sized explorers. And they're cost capped at $250 million for heliophysics. Astrophysics ones are a little bit more expensive. And what that means is if the PI who wins this mission has committed to bringing this mission under that cost. If the cost looks like it's exceeding, there are external review boards, and you're going to say, well, what are you getting rid of in order to meet the cost cap? And if the thing you have to get rid of in order to meet the cost cap makes the mission uninteresting, they will cancel the mission, right? So there's hard constraints on this, And it's been a very effective program for NASA in terms of building innovative instrumentation and having, the responsibility vested entirely on the PI with, very stern oversight from the funders. So this is MUSE, right? These telescopes, again, are going to be built at our institution. There's a spectrograph and an imager. And these are high-resolution versions. The imager is a high-resolution version of the AIA telescopes that we have on Hinode. It's going to have a factor of 10 better spatial resolution and a factor of 10 better image cadence. And then there are spectrographs with comparable resolution that are focused, that allow you to sort of analyze the plasma, the physics of the plasma that you see in the context in the imager. And we'll look at those in a little bit more detail in a moment. And then there's HelioSwarm. And HelioSwarm is an entirely different beast. What HelioSwarm wants to do is look at turbulence in the solar wind. And it's got this, so it's got eight spacecraft of one type and then a hub spacecraft that collects the data and transmits it to the ground. And these external 8 spacecraft can be configured in different shapes to sample the solar wind in different length scales. It's really mathematical. It's really complicated. It's like when I was working on the red team for this, because we have some people who are building the Faraday cups for this as well, and it's like, how is it that you're going to explain this problem in a way that anybody outside of the people who are already on this proposal are interested? But they did it, and it is interesting, and it's really going to be quite remarkable. Excuse me. So first we have MUSE, right? So here's the imager bits of MUSE on the top. This is high resolution data, simulated, but it's going to show you, the evolution of the plasma at different temperatures at the same time, with a cadence of 12 seconds. I'm sorry, this is the spectral rasters. The context images are in a cadence of 4 seconds. So these are images resulting from the spectrograph with 0.4 of an arcsecond resolution, and these are a third of an arcsecond resolution. So we have 2 imagers at 1.5 million and the helium imager, and then we have spectral lines that we're sampling with the spectrograph simultaneously. And the spectrograph uses these slits, so at the same one image consists of spectra along this. For each slit position, you're getting a spectral measurement and a spatial measurement, and they are able to do these in these lines in a way that the spectral lines don't overlap each other, right? So you're able to get a lot of physical information from each of these slit positions as you're taking the context images that are going on behind it. And so it's a technical challenge there, but the images and we're very familiar from AIA with kind of the background of what this is going to look like, and so the MUSE project is looking very specifically at how does the plasma reconnect? What are the implications of that reconnection? How do we see it in the hot channels? Where's the origin? How does the plasma that are contained in the hot channels cool and condense back into the surface? Some of it might erupt out into space. So that's what MUSE is doing, and HelioSwarm is doing these wild things. So these are different planes, but this is sort of different views of the configurations of the satellites. So you can see that there are a bunch of them clustered. The red one is the hub that's transmitting things. And so in this plane, we've got an outlier there. In this plane, they're all kind of in the cluster, and then there's one outlying there. And as they move around the Earth, they sample the solar wind, the Earth's magnetosphere, and the sort of complicated region of the Earth's magnetosphere and interaction with the solar wind, right? This sort of foreshock region. And so the different experiments are going on in different parts of the orbit around the Earth. And so, and this is just another sort of attempt to get the projections here. So what they're interested in is sort of, I measure the plasma here spatially, I measure the plasma there spatially, and I look at correlations between them. And then I look at correlations between this one and this one, this one and that one, and all of these are, this is what they call the baselines. And so different physical processes occur on different scales, and you're able to sample the different scales in space and time with these complex intervals. So that's the plan, and I think that's the end, and my voice is going, so I think it's probably a reasonable place to end as well. Thank you. Questions? Yes? And I will repeat your question because for anybody who might be online, so just, I'm not being pedantic if you... Okay. Complicated question. So I think the question is related to when nuclear fusion is happening, the sun is actually creating heavier elements in that process. And when we are looking at the atmosphere of the sun, do we see evidence of those products of the nuclear fusion and we do, but the time scales are really very different. So the change in the sun's chemical abundances due to fusion occurs over hundreds of millions of year time scales, right? The sun is 4 billion years old. It's going to last another roughly 4 billion years. And it's over those kind of time frames that you get substantive changes in the chemical composition of the star as it evolves. And all of the things that we're looking at, obviously, we're just seeing snapshots. So we are seeing the evidence of, the fact that there's iron, carbon, a lot of those elements were there when the sun was formed because of supernova formation, earlier formation in the universe. So I think that's actually where the chemical composition that we're seeing in the outer surface, now that I think about it, has to be, is from the solar formation, because it's not, the stuff that's changing in the core does not have a chance to precipitate to the surface. It's only through supernova explosions that material then gets out into the rest of the universe and then can condense someplace else into forming a star. But really, that's a very complicated question. Thank you. No, I think it can't, but yeah. It's really the only thing that's able to, you're not getting a churning motion within the interior of the sun, in the core. Yeah. So.
Yeah, you mentioned.
Yeah.
And I was wondering.
Yeah.
Are you seeing?
Yes, it's forecasting the amplitude of the solar cycle has really not been very successful. And part of the problem with that is that there's an 11-year sunspot cycle and a 22-year magnetic cycle. And, somebody's career is only 2 solar cycles long at the most, right? So and instrumentation changes over 40 years. So, we have archival data of sunspots, but it's kind of not constraining. And we have, 40 years of, we have magnetic field measurements since Hale, right? And those are better, but again, the stuff that you really want to know, you've only kind of learned recently. So the constraints are challenging. That said, yes, the solar cycle is more active than the previous one. There was, some 3 cycles ago, things were pretty active, and then there were a couple of cycles where the activity level dropped, and everybody likes to draw straight lines. It's going to go to 0. It's going to, and it didn't. There's some interesting, the forecast model that seems to be working the best for this particular sunspot cycle is one that Scott McIntosh and collaborators have worked on, and they've been looking at sort of particular observations of the origins of bright structures early in one cycle and how those overlap to try to track whether you're going to get and so they had forecasted a big cycle. But again, forecasting one is like, yes, you picked a winning racehorse. Am I now going to sell my house and give you money to pick the next winning racehorse? Probably not, right? So, and he's not going to live to have 10 of these predictions, right? So it's really hard. They're getting better, but I think forecasting, the next sunspot cycle, this one now casting this one, yes, it's pretty big. We know it's pretty big, and that's interesting. But it's still it's hard. It's analogous to forecasting. Put it in very concrete terms. Where is the weather front going to land on April 8th? Is it going to be east of us or west of us, right? That'll tell us whether we have clouds or we don't have clouds on April 8th. And there's kind of a lot of discussion about that too, and it's a really well-constrained problem, but still the physics is challenging. Other comments? Yeah, hi.
Can you just say a little something about,
Sure. Okay, yeah, so when you have big solar events, they generate, so what we understand about the most dangerous solar events is that they happen when you have one coronal mass ejection that kind of empties out the material in the heliosphere between the Earth, say the sun and the Earth. And then another one occurs shortly afterwards that might even be a stronger one. And what happens is the second one is able to accelerate much more rapidly because it's not being constrained by the mass of the material that the first one has cleared away. And so you can end up with this sort of, you have one CME that's kind of typical, and then the next one, because the acceleration is not dampened by inertia of that material, it's really the velocity of that, the magnetic fields and the mass associated with it hitting the Earth's ionosphere that has the big impact. And of course, the magnetic fields have to be oppositely aligned. If the two magnetic fields are in the same direction, the same high velocity stream will just kind of flow around the Earth and have much less of an impact. Associated with these fast-moving CMEs are shocks, and within those shocks, they can accelerate particles. And those high-energy particles can have adverse impacts on people, adverse impacts on satellites, inside and outside of the Earth, even satellites in interplanetary space. One of the things, so NOAA is charged kind of with sort of the Earth forecasting of space weather on the Earth, but NASA has an obligation to protect NASA resources everywhere, right? So on Mars, for example, we have to understand how do you do space weather forecasting when Mars is orthogonal to the Earth, or even, let's say you had a satellite that, people staying on Mars on the opposite side of the sun, right? Their information content for the people who are on Mars to understand their space weather environment, we have to know what is it that they need. And you kind of need to know what is the least amount of things that they need in order to do the observations, because getting anything to Mars is a challenge. And if you can't put the entire Solar Dynamics Observatory in Mars orbit, right? It cost $1 billion here, it'll be, And so you need to understand what observations you need to make to do that remote forecasting. And that I think is one of the challenges for NASA in the coming decade. And part of, and one of the things that the next decadal survey is probably going to talk about, that these are sort of National Academy of Sciences panels, is these multi point measurements across the heliosphere. We're seeing some of it with Parker Solar Probe. Solar Orbiter is out there as well. And, but doing that in a more consistent way to get a grasp of the connectivity and relationships. There's one more weird events in solar physics. So there were two stereo spacecrafts that were almost 180 degrees on opposite sides of the sun from each other. And there were high energy particles from a single flare that hit both of them, right? So these high energy particles are tracked by magnetic fields, but the magnetic fields had these separatrices, so they diverged dramatically from where the flare source is, and one of them went in one direction, and one of them went all the way to the opposite side of the sun, right? The same event created, high energy particles both sides, and the separating of the flares are small, in terms of the sun. So these structures can be really complicated, and it really kind of, that's a frustrating result because that observation you're never going to really know how to constrain that, how those are separated. But we will try. I don't know. Maybe I answered your question somewhere in there, but. Okay, well, thanks.
Thank you very much for your time tonight.
Yeah.
And I hope everybody enjoys the rest of the weekend. And
Getting, I know Rick's up there. No. I hope everybody has a great eclipse weekend and enjoys all of the Totality events, Totality and Tupper events taking place both here at the Wild Center, at Apollo Field, at LP Quinn. And for those of you traveling in, that's 294 Hosley Avenue. Dr. DeLuca will be speaking again at the Apollo site on Monday morning, and in addition to a panel discussion here on Sunday evening. So thank you for joining us online, if you were, and thank you for joining us here. And on behalf of the Adirondack Sky Center and Observatory, have a great weekend. Thank you.